So we say that black holes will open up a new space in the future history of the universe. Our universe began 13.8 billion years ago, and it is widely believed that everything began with the Big Bang. Eventually, the universe began to expand, galaxies formed, stars were born, and planets formed. Life began in one of these galaxies, the Milky Way. By this time, life had evolved to the point where people began to wonder about the origins of life and its place in the universe. But what if everything we know about the universe is wrong? What if the Big Bang wasn't the beginning of the universe? What if we found something other than the result of life in the main world's black hole? A hole. But what is this based on? What does it mean for us to live in a black hole? Join us as we explore a new theory that proves that big cities are wrong and that we have always been in a black hole. Turn back time. Before humans, before the Earth was formed, before the sun rose, before galaxies, before the sun rose and light appeared, there was the Big Bang. This happened 13.8 billion years ago. But what happened before that? Many physicists say there was no before. They claim that time began with the Big Bang, and science has no idea what happened before that. We will never know what reality was like before the Big Bang, what created it, what exploded to create our universe. This idea is beyond human understanding. However, many scientists do not agree with this idea. These physicists believe that just before the Big Bang, all the mass and energy in the universe was compressed into a very dense but small particle. Let's call it the seed of a new world. That seed is very small, probably 1 billion times smaller than any particle that humans have ever seen. But this particle can create other particles as well as entire galaxies, solar systems, planets, and all people. If you want to call something the divine particle, that's right. So how is this seed created? One idea, proposed years ago by Nikodem Poplawski of the University of New Haven, is that the core of our world was created in a very deep furnace, a black hole, nature's most dangerous environment. Before going any further, it's important to note that over the past few decades, many theoretical physicists have become convinced that our universe is not the only universe. Instead, we may be in a multiverse, a collection of separate worlds, each with its own unique sound that shines through the dark night sky. This led to the idea, popularized by Stephen Hawking, that whenever we create a black hole in our universe, we create a microcosm that can only be seen by a passing observer. The point where the black hole falls. Did our universe form from a black hole in some ancestor universe? And is a new universe born every time a new black hole is created? But what is the reason for this concept? Yes, it is very interesting. The characteristic of a black hole is that it has an event boundary. The boundary is a region that shows very different information about what is outside and what is inside. Outside the black hole region, the vibration of the object itself can be felt because the space around the black hole is curved, but this also happens if you move too fast or too fast in the right direction. You do not fall into the black hole, but you escape the influence of the black hole. If an object passes the edge of the event horizon, it dies immediately and appears in the singularity of the black hole. The structure of spacetime inside a black hole is highly curved, so if an object passes through the collision region and reaches it within a few seconds, the mass of the black hole increases during the operation. To those outside the fallout zone, a black hole appears to form and grow larger over time. But what does this have to do with our universe? To take all the known and measurable forms of matter and radiation in the observable universe, you would have to add them all up. Ordinary matter, made up of protons, neutrons, and electrons. Neutrinos, ghostly elementary particles that barely interact with ordinary matter. Dark matter, which dominates the mass of the universe but has so far eluded direct detection efforts. Photons, or particles of light, which carry energy from all electromagnetic events throughout the history of the universe. And gravitational waves, which are created whenever mass moves and accelerates through the curved fabric of spacetime. At the farthest limit of what our instruments can detect, we can see about 46 billion light-years in all directions. Adding up all these forms of energy across the entire observable universe, we can use Einstein's most famous relation, E equals mc squared, to get the equivalent mass of the universe. Then we can ask a somewhat deeper question. If we want, what would happen if the entire universe were compressed into a single point? The answer is that if you compress a large amount of mass or energy into a single point, you would form a black hole. The amazing thing about Einstein's theory of gravitation is that if this mass does not rotate without mass and energy, and does not rotate without angular momentum, then the total mass is the only factor that determines its size. Black holes have what astrophysicists call the Schwarzschild radius. It is worth noting that the Schwarzschild radius of a black hole and the mass of everything in the observable universe are equal to the observed size of the observable universe. This knowledge seems like a coincidence and raises the question of whether our universe is actually inside a black hole. But this is only the beginning of the story. The deeper we dive, the more interesting it becomes. In the mid-1960s, a discovery changed our understanding of the world. A shower of low-energy radiation and an omnidirectional shower of it rained down from all over the sky. The temperature of the radiation was the same everywhere and was currently measured at 2725 Kelvin, a few degrees above absolute zero. The emission was very black-blue and appeared to be of warm thermal origin. Looking at the sky, it was about 1/30,000th of a second. Originally called the primordial fireball and now known as the cosmic microwave background, this radiation provided important evidence that our universe was once hotter and denser and was expanding and cooling. The farther back we went, the smaller, more uniform, and more compact things became. Looking back, this picture of the hot Big Bang appears to be approaching a singularity. This is the same condition found in the central core of a black hole where the density, temperature, and energy are so extreme that the very laws of physics break down. When we look at the equations that govern black holes, something amazing happens. If you start just beyond the event horizon and run infinitely far from the black hole, you will find that the distance goes from the Schwarzschild radius to infinity. On the other hand, if you start just inside the event horizon and trace the distance from the black hole to the central singularity, you will find that the same distance goes from the Schwarzschild radius to zero. Big deal, right? No, it is actually a big deal for the following reason. If you study all the properties of the space outside the event horizon of a black hole from R to infinity, and compare that to all the properties of the space inside the event horizon of the black hole from R to zero, they are the same at every single point. All you have to do is replace the distance r by its reciprocal 1/r, or more precisely, replace all cases of r for r by r for r. Then you will find that the inside of a black hole is mathematically identical to the outside of a black hole. It is almost like picking a 100% reflective sphere, a perfect mirror, and realizing that the entire universe outside that sphere is now included in the mirror image reflected on the sphere's surface, albeit distorted. In recent decades, as our understanding of the universe has improved and improved, two new discoveries have shaken the foundations of the Earth. The first is globalization. Rather than breaking away from independence, it seems that the world was formed by the speed and intensity with which the settlement expanded into a fortress. The shape of the universe gave internal energy to expand, causing the planets to rise, and when the rise was over, a big explosion began. The other is dark energy. As the universe expands, it contracts, and distant galaxies move away from us at an even faster rate. Again, on a smaller scale, the world still seems to be a kind of energy that exists in the universe and does not want to be diluted even though the universe continues to expand. People suspect that if inflation and dark energy exist, there may be a connection. The fact that there is a big difference in the expansion rate of the early universe and the later universe can be explained by inflation and dark energy, but this is only a partial answer to the question. The other part of the question is about the mathematical structure of inflation and dark energy. Both are similar to the equations for black holes. The point is this: there is a remarkable symmetry between black holes and the universe, especially when you think about how these objects appear at different times.